Hello, good evening. It's a great pleasure to introduce and have here Professor Attali. He's a professor of physiology at Attali Medical School in Tel Aviv. He received his master's in physical chemistry together with Doctor of Pharmacy in the Paul-Sabatier University in Toulouse. And then he immigrated to Israel in 1983, received his PhD in neurobiology in Weizmann Institute. He did his postdoctoral fellowship with Michel Ladunsky in France. He returned to Israel as a senior scientist in the Weizmann Institute, and then since 2000 he's tenured professor at Tel Aviv University. Thank you very much.
Thank you very much.
Welcome.
Thank you for inviting me here in ELSC, almost in the new building. So today I will discuss with you some interesting data that are not yet published. They are actually part of the data are in review in PNAS. They didn't want to in Nature Neuroscience, but doesn't matter. So today I would like to discuss how perturbation in the M channel will lead to a kind of biphasic homeostatic plasticity. One which is related to intrinsic properties and to the axon initial segment, and the other which is much slower, which correspond to a kind of slow synaptic scaling. So as you know, neurons are utilizing various mechanisms, homeostatic mechanism to stabilize the firing rate in response to bidirectional perturbation, like increased activation or lower activation, that deviate the network activity from a defined set point. And this change or these mechanisms will involve changes in intrinsic properties, in the EI balance, in synaptic strength, synapse number, and more recently, it was found, something like 7 years ago, that the axon initial segment is also a hub for plasticity. And of course, this will lead a rescaling of the input-output of the neuron. And for example, here, if we have a decreased activity, kind of activity deprivation, we have as a compensation or adaptive mechanism, we have an increase in the excitatory load here, or a decrease in the inhibitory load. And for example, as another kind of mechanism, it could be also an additive mechanism, changes in the intrinsic properties with kind of increase in sodium channel activity or decrease in potassium channel activity. Yes.
The initial action segment, it's now thought that it's only during development, right? That, I mean, nobody could replicate results in adult.
Results in?
Adult animals.
No, there are data in adult animals.
Really?
Yeah. An example here. Actually, as the concept of the action initial segment as a huge center for plasticity, for many years, actually plasticity was studied in the dendritic tree and spines, and more recently, just 7 years ago, it was in 2010, two articles back-to-back in Nature were published, where for one paper, Kuba et al. Showed that auditory deprivation, so when they were dealing with chicken, they removed the cochlea.
But this is during development.
During the development, but there are some data in adult. There are some data in adult. In terms of plasticity, development, the action initial segment is developing. There are many plastic changes in the development, but in terms of adult, there are papers. I'm even reviewing one paper which deals with adult. So
we can talk later. I have contact with Matthew Grubb, and I've argued a lot with him.
I have also several problems with Grubb. So they remove the cochlea, and then, of course, this leads to decreased excitability, and as a result, they found in nucleus magnocellularis, which are the second-order neuron in the auditory pathway, they found that as a compensation, as a plastic or homeostatic change, the axon initial segment was increased in length in order to compensate for this hypoexcitability and provide more excitability to these second-order neurons. On the other hand, there were also paper by Grube and Burone in King's College, and they found in primary culture hippocampal neuron that when they did chronic depolarization, which is a kind of treatment that I don't like that much, for several days. Actually, I just forgot to say that these compensation were on the day scale time. It takes several days, 3-4 days, in order for this change to occur. And here, in the case of the primary culture hippocampal neuron, they found that chronic depolarization, which acutely leads to hyperexcitability, will lead to compensation in the location of the axon initial segment. The length doesn't change, but there is a distal relocation of the axon initial segment, as if these adaptations were occurred in order to compensate for this hyperexcitability. And again, this took 2 days. Yeah.
But the arrows that scan exactly the opposite, right? That if you
These are 2 papers that were dealing with opposite perturbation. One is
that if the axon initial segment will be further away from the soma, then the excitability will be larger.
this is a very big question that we will discuss along the lecture. This is very important. Okay. So our goal was to try to trigger plasticity by targeting not with a kind of general trigger like high depolarization, because high depolarization cannot allow, for example, the experimenter to compare what happens in acute condition as compared to a chronic condition, because in acute condition, when you depolarize with high potassium, you just lead all the sodium channel to inactivation, and you cannot really appreciate the acute treatment. And it's a kind of brutal treatment, because recently it was found that high potassium disrupt the structure of the axon initial segment. This is a very important point. So we wanted to target the M channel, the M-type potassium channel. These are voltage-gated, slowly activating and non-inactivating potassium channel. So why the M channel? First of all, they are located in the somatodendritic tree. Their expression is relatively low, but they are highly expressed in the axon initial segment and also in the node on conveyor. They are fine-tuner of excitability. They are a kind of brake for excitability. They are not responsible for repolarization of a single spike. They are much more important for burst behavior, and they actually act as a brake for this bursting behavior. They are also important because they are mutation in human that leads to epilepsy and epileptic encephalopathies, kind of autism behavior. They are also important for the theta resonance in CA1 pyramidal neuron. They are negatively modulated, that's the name, M current, muscarinic. They are negatively modulated by muscarinic agonists. And as I mentioned before, they allow the network to fire spontaneously. They do not, neutralize the whole circuit, the network. When you are using high potassium, you cannot really appreciate the excitability of the network, because you depolarize everything. Okay. So in our system, I will present data both in cultured hippocampal neuron, in primary cultured hippocampal neuron, and also in CA1 pyramidal neuron from hippocampal slices. And we actually, in the data that I will present, we partially blocked the M channel with a blocker, a specific blocker. The name is XE991. Or we used muscarinic agonists like carbachol or oxotremorin M. Okay, OXO M. We are doing also in our lab the reciprocal experiment to analyze the bidirectional plasticity by using an M channel opener. Okay. So we wanted to make sure these are experiments in cultured hippocampal neuron, and we recorded the M current. This is an usual protocol. You hold the cells, the neuron at minus 20 millivolts. At this potential, you inactivate most of the inactivating potassium current, the IA, And of course, we have a cocktail to inhibit other conductances, sodium, calcium, etc. And then you repolarize the cell at minus 40 millivolts, and then you see the tail of the potassium current. This is the M current. And when you apply acutely the blocker of the M current at 10 micromolar, XE991, you suppress by about 70 to 80% the current density. Okay? And when you apply this blocker acutely, you see that the spontaneous firing of the culture, the hippocampal neuron, is increased, of course. You have an increase in the firing. We also applied, so this is the goal of the study, we applied for longer exposure, not acutely, but for several minutes and even 1 hour, up to 2 days. And under these conditions, the channel is blocked. Okay, there is no kind of modulation or upregulation of the channel. The current, the M current, remain blocked. Okay, we wanted to make sure that extended exposure to this blocker does not degrade the blocker. Is the blocker stable? So this is something that we wanted to check. We put the blocker into this culture, and we checked. Then we took the supernatant of this culture, and we checked on other fresh culture that indeed the blocker, which was previously incubated for 2 days in with the hippocampal neuron, was indeed acting as a blocker. So, and you can see here in this fresh culture that before the treatment we have this kind of spontaneous firing, and after the treatment with this pre-incubated blocker, the cells respond to a higher firing frequency.
The initial cell, the unlactose, you put this supernatant on a fresh, naive culture. What happened to the other culture that lasted 2 days?
The culture that were incubated with a blocker?
Yeah.
No, we know what happens. I will present that, but we just use this soup in order to see whether the blocker is stable. So this was an important control for us to start the experiment. So we focused and this is the first part of the talk. We focused on the intrinsic properties. Okay, so we looked for the threshold current. We looked for other parameters, the frequency of evoked spike discharge, the input resistance, the spike amplitude, the width of the spike, etc. You will see in a minute. Acutely, we are getting exactly what we would expect for an M-channel blocker. So we get a hyper-excitable picture, which means that we have a decrease in the threshold current. Okay. For example, here in this experiment, we have an increase in the evoked spike discharge of this hippocampal neuron. What else? Here in the other properties, we have a depolarization of the resting membrane potential. We have a decrease in the spike amplitude. This is something counterintuitive because actually the M channel allow higher sodium channel availability. Okay, so and this is part of the problem in the location of the action in short segment, and also in the node of Ranvier. We have an increase in the spike width. The input resistance is increased, but then, so this was for the acute treatment. Then when you allow the blocker to stay in the culture, to be incubated with the neurons, one can see that progressively all of these changes will bring the values, all the values, the resting membrane potential, the input resistance, the threshold current, all the parameters back to the initial parameters as if the neuron were not incubated acutely with the blocker. Okay? And this takes quite a short time. When I talked about the 2 seminal studies in 2010, it took them 2 days or even 3-4 days in the chicken, for example, many days in order to get this compensation, this homeostatic compensation. Here we are talking about even 1 hour. At 1 hour, the threshold current is not anymore significantly decreased, as you can appreciate here in acute condition. Okay, and also when you look at the frequency of spike discharge, this takes 1 hour. Okay. 10 micromolar. Yeah. Yes.
Follow the same neuron over 2 days, or each one of the time points is
No, these are separate, of course. We need a lot of statistics in order to get all of these.
My point is that there's a lot of scatter. You don't really know that the neuron who decreased, for example, its expression potential amplitude, recovered it. It could go anywhere.
I agree with this is a limitation of the system, but I will show you data in slices where the neuron were their own control. Okay, so in slices it works and we get exactly similar data. Okay, so these are for all these parameters. You can appreciate here the resting memory potential, the amplitude. All of these parameters are slowly, progressively returning to their initial values. But again, we are talking about our time scale and not their time scale. We got similar data with Carbachol, for example, and also with the OXO-M. So we got this relatively fast adaptation or fast homeostatic change that bring the values back to their the initial condition. These are again the same things with Carbachol, for example. Okay. Now, it was very important for us, since we were looking or zooming on the intrinsic properties, and we targeted the M channel, so we know that the M channel is located in the axon initial segment. So we wanted to look what happened to the axon initial segment and to the location of sodium channel, voltage-gated sodium channel, and the voltage-gated potassium channels that are responsible for the building of this M channel. So the names are quite barbaric. So this is the KV7.3 and the KV7.2 channel. These two subunits will assemble the M channel at the axon initial segment. And as for the sodium channel, because we didn't have at that time, now we have more specific antibodies, but we used an antibody that was a kind of pan-antibodies for all the sodium channels. I just remind you that in the axon initial segment, two main isoform of voltage-gated sodium channels are present. In the proximal part of the AIS, of the axon initial segment, we have the NAV 1.2, and in the distal part, we have the NAV 1.6. Important, the NAV 1.6 has a lower voltage threshold, voltage value for activation, so it activates at lower voltages. And this channel, this NAV 1.6, is the one which is responsible really for the spike discharge at the axon initial segment. Okay? The NAV 1.2 is considered as important for the back propagation of the spike that was initiated in the axon initial segment. So when we look at the location, we find that actually compared to, and again, these are not the control of the same neuron. We could not, but now we have tools. I will discuss this later. We have now tools to follow in live imaging the channel. So here, under untreated condition, we have a location of the KV7.2 in the axon initial segment. It starts at about 6 micrometers from the soma, okay? But then, after just 1 hour, we can see that the length, all the slot of the KV7.3, so the M channel, is moving away from the soma, okay? This sliding is about 4 to 5 micrometers, okay? We have exactly the same feature with the sodium channel when we labeled it with the pan-NAV. So we have this distal relocation of about 5 micron away from the soma. The length, the total length of the M channel and the sodium channel doesn't change. I have to mention that the sodium channels, the length of the sodium channel slot is longer. They start at about the same place compared to the distance from the soma, but they are longer in the distal portion of the slot, which means that you have more sodium channel in the slot in the axon initial segment compared to the KV7.3. Okay?
I think we'll listen for Uncle G.
In a minute.
There's a small decrease in the AS length after 1 hour.
After 1 hour,
Yeah.
For what? For sodium?
Yeah.
This is
No, in the length.
In the length. No, this is not significant. No, we have many experiments. We are talking about hundreds of cells that we are analyzing. So you need large numbers because this is very... we get exactly the same feature with carbachol. Okay, again, distal relocation of about the same length from the soma with carbachol. And again, we are talking about our time scale. Okay, these are our time scale. You look at the of the times. We wanted to know whether the process is reversible. Okay, so we took the cells, we treated with the XE991, the blocker of the M channel, and then we washed out for several hours, for 24 hours, and we could get back the distal relocation was again recovering and getting more closer to the soma as in initial conditions. Okay. Now, what happens with ankyrin G? As I mentioned, these channels are in the development, and this is really a very important developmental process. So in the development, when the axon is growing, when the axon initial segment is actually becoming specified at the proximal part of the axon, there is appearance of one very important protein which is called ankyrin G. Ankyrin G, and the root of the Latin root of ankyrin is just an anchor. So this is the glue that allows these channels, both sodium channels and potassium channels, to be anchored in the axon initial segment, anchored and clustered in high numbers in order to provide their localization, their specific localization in the axon initial segment. And what happens with ankyrin G? So with ankyrin G, at these time scales, at the hour time scale, ankyrin G does not move. Okay, you have to wait 2 days in order to get the slow motion of ankyrin G by about the same distance, about 5-6 microns. Okay, so this is an important point because you will see later that this kind of slow kinetic may fit with other changes that are apart from the intrinsic properties, but are related more to synaptic processes. Yes.
Why do you say this moves? I would think that
It
something
slides.
else moves, that something else pushes it, the extended segment.
So you can say maybe the axon is growing, this part of the proximal axon, but it does not, because the total length of the slot for the channel doesn't change. So this is not compatible with the growing of the axon. But something is related to the microtubules. I can tell you that these moving are prevented by incubating the cells with Taxol. 100 nanomolar of Taxol totally prevent. Taxol is a stabilizer of the microtubules, so it's as if when you have this motion, this sliding of the channel along the axon initial segment, you need some kind of depolymerization, some kind of disassembly of the microtubule. It's something which is amazing because it's difficult to imagine in terms of the mechanism that all these slot of channels, the hundreds of channels or thousands of channels are moving, are sliding, because the axon initial segment is very well known that it is a kind of diffusion barrier. There, at the axon initial segment, molecules, protein of course, and even small molecule lipids are not moving. The diffusion coefficient is very different as compared to the cytoplasm. So it's a very important diffusion barrier. It is also a filter, kind of filter, because the vesicles, the somatodendritic vesicle cannot penetrate into the axon because the axon initial segment is a filter to prevent the entry of vesicles from the of origin of somatodendritic compartment to penetrate into the axon. So it's difficult to, yeah?
You could blow something from the soma, and you could push it from the soma.
That's possible. We are looking for motors. The motors are very important, okay, the motor protein. So just in order to understand the physiological impact to this sliding of both sodium channels and potassium channels, we wanted to know, we used Actually, the sodium influx, and this is thanks to Ilya Fleiderwich. So we collaborated with Ilya in Beersheba. So my student was always going to Beersheba, so he knows very well the train to Beersheba. And he was doing, because there he has the equipment in terms of the laser, the good wavelengths for the laser, by using a fast or high-speed fluorescent sodium imaging. Okay, we use the SBFI. And the SBFI has a relatively low affinity for sodium, something like 20 millimolar for sodium. The basal, the intracellular sodium is about 4 millimolar, and we are in a very good dynamic range in order to see what happens in terms of this sodium flux when we are using the SBFI as a sodium probe to actually to reflect the sodium influx. There are also problems of diffusion, lateral diffusion, but we are in this experiment, with this kind of experiment, so usually Ilya was doing this in cortical slice. We did this in primary culture of hippocampal neuron, and this was really a tour de force because it is quite difficult to localize first the axon. You have to identify where is the axon. In order to do that, so we have a patch electrode which is filled with the SBFI, and we provide trains of single action potential, because this presents the lateral diffusion. And of course, we are looking at the axon. Once we identify the axon, we could see in terms of the signal that when you have a sharp rise and a very fast decay of the signal, that it is indeed sodium transient that reflects the sodium influx into the axon. Okay? And as you can see here, these are the control conditions. This is the sodium transient, if you wish. We are analyzing what I would say. It's not a relative delta F. It's really the real delta F. It's not delta F over F. Okay, because really this reflects the sodium influx. And you can see here under control conditions, so this is the spike that we triggered into the patch electrode, and this is the fluorescence that is recorded, that is acquired in the axon. And you can see this under control condition, we have this sharp increase in the rise, and then we have this maximum sodium transient, and you have this splay out, this distribution of this sodium transient, okay, along the axon-initial segment. Under treatment for 4 hours with the blocker of the M channel, so we have things which are changing. First of all, we have a wider distribution of the sodium transient, and then the peak of the sodium transient was shifted away from the soma by about 8 micron. When you look at and this is a statistic, we made a lot of statistics, and we have really a distal relocation of the maximum peak of the sodium transient using the SBFI. Then, this is an example on the same neuron. You can see that the acute application of the blocker does not change the maximal peak of the sodium transient, but after already 30 minutes, half an hour, you see this sliding, this distal relocation of the maximal peak, reflecting the sodium influx into the axon-initial segment. So it's a very fast process.
So this is the same cell.
The same cell. It's really amazing because it's very fast.
How do you distinguish between axon and dendrite? Because you should have also sodium influx.
No, in dendrite and in the soma, you have, first of all, the signal is much lower. In the soma, the signal is enormous, okay? But you don't have the change. You are looking for changes. So and in the soma, you don't have transient. In the axon-initial segment, in the axon you have the transient, okay? So and of course, Ilya is very well. He has the experience to look for that. We made a lot of controls in order to prevent any kind of diffusion, lateral diffusion. Okay, so this is an event that appears very quickly. Then we wanted to, this is a control. For example, in this cell was not treated by the blocker of the M channel, and you can see that more or less the transient and the distribution of the sodium transit is the same. So there is no disruption by, when you have the patch electrode and you have dialysis or metabolic problems or something like this. So the signal is kept constant. So then we wanted to know where exactly, so we were looking for the sodium transient, but we wanted to know where is the spike trigger zone, where is the spike is located, okay? And of course under control condition and under blockade of the M channel. So for that purpose we used dual patch recording. So we have an electrode, a patch electrode in a whole cell configuration that was patching the soma of the neuron, where we filled the electrode with SBFI, again to see where is, to identify the axon, and to provide the trigger of the spike, of single spikes. And here we have a loose patch electrode, so an extracellular electrode, that allows us to move along the axon initial segment and to measure the action current along all the length of the axon initial segment, okay? And doing that, we could actually measure, record the action current. We normalize, of course, the action current are decaying as far as you get farther from the soma. We normalize the action current and compared the delay, the lag, between the occurrence of the spike in the soma and the occurrence of the action current along the axon initial segment. And of course, the trigger zone is defined as the maximal lag between the occurrence of the spike in the soma and the action current along the axon initial segment. Okay, and we found that actually here under control condition we have the trigger zone which is located at about 21-22 micron from the start of the axon initial segment, and under incubation with the M channel blocker for 4 hours, we have again a distal shift in the trigger zone. Now we are talking about the trigger zone. Okay, so this is again we are talking about of hour time scale and not day time scale. So it's relatively fast. So then we got we worked. So Yoni was working on the hippocampal slice, and he was recording CA1 pyramidal neuron. And under these conditions, so he was looking for the intrinsic properties. And first, for example, in this CA1 pyramidal neuron, on the same neuron, he was treating acutely the CA1 with the M channel blocker. So you can see under acute condition, the threshold current is actually diminishing. But then you can follow all along the recording in the slice, and the slides were okay for more than 2 hours. And we could see that after 2 hours, 2 hours and a half, we have this adaptive change that actually, this is for example for one neuron, and this is the statistics for many neurons. So under acute condition, the threshold current was diminished, and then again back to the initial value after treatment of 1 to 3 hours with the M channel blockers. And you can see here on this one example of one neuron, you see that we have first a decrease in the threshold current, and then progressively the threshold current is regaining its initial value. Okay, the same for the evoked spike discharge. And an interesting feature that maybe reflects what we see as a distal relocation of the spike trigger zone is the phase plot. When you evoke a spike into the CA1 pyramidal neuron, you can see that acute treatment does not change the phase plot. Okay, so the occurrence first of the axonal spike and then the somatic signal. Under chronic exposure, so 2 hours and a half with the M channel blocker, you can see that we can get here this kind of bump. So we have the axonal signal which occurs before, so at shorter time and at lower potential. So we shift here the threshold voltage for the occurrence of the axonal spike, and we have a longer interval between the two peaks, the axonal peak and the somatic peak.
What will happen if I wash now the blocker
Yes.
and record the spike immediately after the wash? I mean, before the plasticity comes back, being the
You mean expose acutely with the blocker and then wash?
Yes.
We didn't make this experiment.
The question is whether this result is related to the fact that you don't have the M channel, or it's just a matter of accessibility of moving that.
No, the M channel are present. You see here the change in the. I mean, we have M channel down. I mean, CA1.
I understand, but the fact that the voltage threshold
changes. Yeah.
is due to the fact that you shifted the initial segment far away. Right, so you have less.
Not at far. You mean after a longer extended exposure? Yeah, 2000. Yeah, maybe. Yeah, this is a control that we have probably to do. Yeah. But we did controls with non-treated slice, for example, for the same period of exposure. So the slice was stable. We had really the nice control with these CA1 recordings. Okay. Yes.
So when you apply XC on this slice, you should also expect spontaneous firing.
Yeah,
right?
but we used, it depends, 10 micromolar, I don't know. CA1 are quite difficult to fire spontaneously with 10 micromolar XC.
I think so. The paper by Baker Sharp, it showed that it fires spontaneously.
Depends maybe how you cut and where. I mean, we didn't observe some. No, right. In some cases, we may get some spontaneous firing. Yeah, you're right. No, I recall that sometimes Yoni told me that he gets spontaneous firing. But this is not a very systematic observation that we got.
In any case, the members should temporize.
Yeah. We have exactly the same. I don't show all the parameters that the intrinsic parameters that we recorded, but these are exactly the same feature that we got from culture deportable neuron. This is the label of the channels, sodium channel, potassium channel, and the M channel in slices, and we see exactly the same features. So distal relocation. Here we have the KV 7.3 under untreated and treated conditions. The nav channels also, and we have this kind of, it's about 2.5 or 3, and it goes. We have a distal shift of about 4 micron. Okay, the total length doesn't change.
What do we see here? I don't understand the data.
This is a new N label. Okay, this is a low magnification. You see all the CA1 pyramidal neuron here, and what you see, this straight line are the axon-initial segment. Okay. You see here this is a higher magnification. Okay, I'm sorry. And here these are the sodium channels. So you see this straight line, the green one, which are the sodium channels. So we have distal relocation for both sodium and potassium, with no change in the length, the total length of the slot of this channel along the axon-initial segment. Then we wanted to know what kind of mechanism we could, let's say, could hint about some important feature of this kind of observation. So we checked, for example, protein inhibitors. It does not require protein synthesis. Okay, we use this cyclohexamide to block the protein synthesis, so it does not depend on protein synthesis. This distal relocation. We checked for voltage-gated calcium channels because the group of Grube and Buonis found that in their experimental setup that probably the voltage-gated calcium channels were involved. They are not involved in our case. We found just one important parameter that was important for this distal relocation, and we used a blocker of the enzyme, the kinase, which is called casein kinase 2. Casein kinase 2 is a very important enzyme, a very important kinase. It's highly expressed in the axon-initial segment, and it is really a central player in the formation during development of the axon-initial segment. Okay. As you can see here, when we used TBB or TBCA, these are two different blockers of the CK2. You see under normal condition, so we have untreated, and you have the XC, the blocker of the N channel. You have this distal relocation, significantly different here. But when you apply the TBB, you prevent this distal relocation of the potassium channel. The same with sodium channels. This is also for a sodium channel. What else? Yeah, in electrophysiology, what we could find is that when we are using TBB, so the blocker of the casein kinase 2. So here is the treatment for 4 hours with the TBB. We have a slight increase in the threshold current, but when you apply both the TBB, the blocker of the CK2, and the blocker of the M channel, still again you get, as in the initial condition, you have a decrease in the threshold count. So you get this change after a 4-hour treatment with the blocker of the M channel. And this is the spike discharge. So in summary, using a blocker of CK2, you can prevent this distal relocation of the potassium and sodium channel, and also the feature of the intrinsic properties when you block the CK2. Yeah.
You have in mind something like a sliding telescope base which requires energy to pull out?
We are looking for this mechanism, and we are now really investigating this kind of mechanism, because there are many. For example, CK2 will phosphorylate the channel. This is known. They phosphorylate sodium channel and potassium channel in order to anchor them to interact with the anchoring G. Okay, so this is a very important kinase in this germ. Then CK2 phosphorylate calmodulin, because it interacts with these channels, and then it will increase the interaction of calmodulin with the channels. CK2 interacts with the motor protein, KIF5. KIF5 is a crucial axonal motor protein that is important to, so it activates this motor protein. Something is related to microtubule and to the motion along the microtubules. CK2 confers microtubule stability in a phosphorylation independent manner, and CK2 is also known to phosphorylate HDAC6, which is a deacetylase, and is also important for tubulin stability. Okay, so this is what we know about CK2. So just to summarize this very quickly, this part of the fast process, of the fast adaptive change that we can see upon incubation with the M-channel blocker, we have here, and so this summarizes actually the slot of Kv7.3 and sodium channel. As I told you, sodium, the length of the slot for sodium channel is slightly longer than the potassium channel, and anchoring G is even longer. Okay, anchoring G overlap the whole slots for the 2 channels. Okay, then following short treatment, a matter of few hours, we have this sliding of the 2 channels. They go together. This is important because these 2 channels are physically interacting. A recent paper published in PNAS by Jeff Pitt showed that the 2 channels are linked, are bridged by a protein which is very important. It is called FGF14. FGF14 is linking sodium and potassium channels. It acts as a unit. It's a structural and also a functional unit. Okay, and then after a longer time, we do see this sliding of anchoring G. Okay.
So you know for sure that it doesn't slide beyond the anchoring G?
No, for sure. This we check it very, very carefully. Yeah. So then we try to play around to see, and this is a question, a big question of how can we envision this distal relocation of both sodium and potassium channel, and Ilya was working on this issue by just considering sodium channel, and of course it is very rational to envision that slight distal relocation of sodium channel, only sodium channel, will provide more excitability, okay, because it will get far away from the capacitive load of the soma. And then, of course, the spike will fire easier when you remove a little bit from this big capacitive lobe of the soma. Okay, so here we try to model by considering so the distal location. We played with the location of the 2 channel from along the axonal segment and with different distance from the soma. And considering only sodium channel, or sodium channel and M channel. Okay, so here, for example, first of all, the slot. So it's a very basal modeling. It's not this is totally incomplete and probably completely wrong in terms of the details, because it may be possible, and this is also a very interesting issue, that during this plastic process, the plastic process, not only the channel are sliding, but maybe the diameter of the axon is changing. Again, there is a recent paper showing that during activity, the axon is breathing. They are kind of enlarging of the diameter of the axon. So we have to take many parameters. But just to be very simple and primitive modeling, so we put a slot of 30 micron for the axon initial segment for both sodium and or M channels, and we put this location of this channel at 5 micron or at 15 micron away from the soma, okay? And then we allowed a conductance of 1,000 picosiemens per micrometer square for the sodium, and we varied the density of the M channel from 1 to 3 compared to the value of the sodium. Okay, so we try to just vary a little bit the density of M channels in favor of the M channel by 1 or by up to 3 times the value of sodium channel. So when you look only for the contribution of sodium channel, okay, and you look at the location of sodium channel at 5 micron away from the soma, okay, when they are located at 5 micron from the soma, you inject current, so we fix the resting potential at minus 68 millivolts. You have this spike, and then when you take exactly the same injecting current, the same trigger for the spike, you get, when you locate the sodium channel farther from the soma at 15 micron instead of 5 micron, and you have only sodium channel, then we get an increase in the excitability.
Where do you inject the current?
What?
Where do you inject?
No, it's a model. In the soma.
No, I know. I think the model. Where you inject the current?
In the soma.
And you got the lower threshold when you remove the channel farther away?
Yeah. And all the cell has passive properties except the region of the axon initial segment, this 30 micron, with a diameter of 1.2 micron, and I mean the active part of the
but the basic property of passive cables say that if you make it farther away, you will have less voltage.
No, because you have differences in the capacitance. The diameter, the capacitance of the soma is huge. So when you get a little bit farther, it's not very far away. So when you get a little bit farther from the soma, you facilitate actually the firing.
At the point where you have the sodium channel,
yeah,
you should have less voltage. Why you get the electric potential?
But the voltage threshold will be lower.
The threshold will be lower.
You don't change the concentration of the channel.
No, we don't change. We don't change the concentration of the channel.
Why the voltage should be lower?
Because it is linked the axon and the soma.
And the soma.
Nicky showed this 17 years ago.
Yeah. No, this is a. But then, when you take into consideration both the sodium channel and the potassium channel, which is actually the real case, because this is the case, okay? Then, when you get this slot at 5 micron, both potassium channel and sodium channel 5 micron away from the soma, you evoke a spike. First of all, it's less excitable because you need to inject 1.2 nanoamp compared to 0.23 nanoamp here. Okay, so you evoke the spike, and then when you get a bit further away these two channels from the soma, you get really lower excitability. Okay, so in other words, when you and this is, for example, the threshold, the value of the threshold current. When you have only sodium channel, you get a low, so you get hyper excitability. You have lower threshold current. But when you couple the two channels, you increase the threshold current because you have both contributions. But again, the M channel, this is something I'm not at all happy with this with the model and with the experiment, because we know that M channels have a kind of dual role. For example, the M channel on one hand will lower the resting membrane potential. Okay, so it has a strong impact on the resting membrane potential. On the other hand, it will facilitate the recovery of sodium channel from inactivation, so it will make much more sodium channel available. For example, why do we have co-localization in the node of Ranvier, and this is for saltation? Why we have both presence of sodium and potassium, and these M channels, these are the M channels. We have heat together because they have actually a role in facilitating in a way the excitability. So in the axon initial segment, it's a kind of balance, depending on how much you are far away from the soma. And of course, in this case, we are in the configuration where the distal relocation of these two channels together will lower the excitability at this range of course, of distances.
Is there a difference in the kinetics of the two channels?
Oh yes, the sodium is much faster.
Yeah, so how come, and this fits with your model?
Yeah, all the kinetics were introduced in the M channel is much slower, and it fits. This was introduced into the model. This is a model that was used also for many other. Martin Cole has used this model also. Then, just maybe 5 minutes. I have 5 minutes.
Yeah.
It's okay.
But there are a lot of questions.
Okay. So then, at that stage, so we had a relatively fast process, fast adaptive change. Okay, a matter of hours. Especially and mainly the intrinsic properties and this distal relocation of the channels in the axon initial segment. Then we had a slower process. I talked to you about the spontaneous firing rate. This is the acute exposure of the M channel blocker when you look at the spontaneous firing in this hippocampal neuron. But then when you look at these parameters, you see that this is the acute condition, so we have an increase in the spontaneous firing, and then when you apply the drug for more and more time, you see that after even 1 hour, here. So you have still after 1 hour, 4 hours, even 24 hours, an increase in the firing rate. But then after 2 days, we have a resetting of the initial value for the spontaneous firing rate. So we have a slow process that is also taking place in addition to the changes in the intrinsic properties. But then and this is a thing that we are very much interested, we analyze the bursting. So the mean firing rate is adapting, but it takes 2 days. Okay? So you see, this is the firing rate, and it takes 2 days to bring back the values to the initial one. Okay? But then when we looked at the burst, these are poor patch clamp experiment, and we are now starting experiment with Ina Slutsky because we want to look at the whole network. Okay, so just a very gross examination of the burst, we see that under acute condition we have more burst in a unit of time. Okay, but the whole mean firing rate does not change. It increases. We have an increase here in the bursting, and then we have a fast adaptation. After 1 hour, we have less burst. So the increase in the bursting is returning to the initial value. Then, Boaz in Ina's lab we are starting really now to look at this process. So we put the hippocampal neuron on MEA, and we look for 2 parameters, the mean firing rate and the bursting. Okay? In the mean firing rate, when you expose the cells to the M channel blocker, you see that we have an increase in the mean firing rate, and then we have a slow process of kind of homeostatic changes, and you see you need at least more than 1 day in order for the value to return to their initial value. But then when you look at the bursting, you have first an increase in the bursting under acute condition, and then you have very fast release or depression of the bursting. So these are, of course, totally preliminary, and we have to really look at this feature very carefully, because this this focus us on very important issue, and you are many here looking for this issue. When we are talking about homeostatic process, we are talking about a network, but we are also talking, and the stability or the robustness of the network, and is it an addition or an increment of individual neurons, or is this something that actually take into account about very unstable or very variant individual neuron, and then when we look at the whole network, we have something which adapts with a certain kinetics, something that is happening with two kinetics. And this is illustrated by this. For example, if you look at the spontaneous EPSCs, okay, under acute condition we have an increase in the spontaneous EPSCs, and then it adapts, and it takes about at least 1 day in order for the spontaneous EPSCs to return to their initial values. No change in the inhibitory spontaneous iPSCs, okay? We looked for the minis, and especially for the excitatory minis. So for the mini EPSCs, we have just one parameter that after 2 days, and it occurs only after 2 days. After 2 days, we have a decrease in the amplitude of the mini EPSCs, and not after a few hours, like the change that we observed in the axon-ischial segment and the intrinsic property. So this takes 2 days, okay? So we have a decrease in the amplitude of the minis EPSCs. We have also a decrease in the tau of the minis. I'll go very fast. We looked that maybe under these conditions for 2 days incubation, we have a change in the number or in the ratio of the excitatory button or inhibitory button. It doesn't change. The EI balance doesn't change. We looked at the, of course, in electrophysiology. This is here, I think. Just a minute. Yeah, this is the EI balance. In acute condition, it increases, but then it will stay. It doesn't change following longer extended incubation. Then we looked at the spine density, and only after 2 days we get a decrease in the spine density in these neurons, and we have also a decrease in the GLUR2 positive spine in this hippocampal neuron, and it takes 2 days. So we have kind of fast process that is linked to the intrinsic properties and probably to the axon-ischial segment, so this relocation of the axon-ischial segment. But then we have a slow process that involves other synaptic markers or synaptic players, okay? Okay, just to conclude, we have the prolonged or extended incubation with the M channel blockers that produce a rapid adaptive change from 1 to even half an hour to 4 hours. So change in the intrinsic excitability of CA1 pyramidal neuron, we have seen both in slice and in primary cultures. This is accompanied with the same kind of kinetics, time scale of hours, with a distal relocation in the spike trigger zone and also on the sodium flux and the sliding of the sodium and the N channels, the Kv7.3 channel. The rapid structural and functional change at the axon-ischial segment are dependent on the crucial AIS player, which is the casein kinase 2. It's a very important player in this region of the axon-ischial segment. A prolonged incubation with the N-channel blocker will produce slower homeostatic synaptic processes, which include the mean firing rate, the decrease in the spontaneous EPSCs and decrease in the amplitude of the mini EPSCs, and the decrease in the GLUR2 positive spine density. So, just to conclude, when we are just disturbing the M-channel activity in these neurons, we are triggering a biphasic homeostatic process compensation, one which is fast and it involves a relocation of the axon-ischial segment, and another one which is slower, and of course this involves other synaptic contribution. And what we are interested in is that in the firing pattern, okay, the fingerprint of the firing of these neurons, what happens, and using of course MEA, we would like to know what happens on the long range and in the short range, what happens to this fingerprint of the discharge of this neuron when we are disturbing this M-channel activity. So just to thank all the people that really made the work. Yoni is really the strong contributor of this work. Eti Patrick, Leah Shalom, she's now regarding investigating the other side, I mean the other direction, the lower excitability using an M-channel opener. Asher Peretz, Maya Lipinski, and in Ben Gurion, Ilyav, of course, and Yana Krapunski. So thank you very much. Yes.
Kindness has a critical role. Is it known if this kindness is regulated? How is it regulated?
No, this is a very important question. It's not regulated, it's just there. I mean, it's not an induced... At least what is known in the I looked very carefully in the literature. This is a kind of constitutive kindness, which is not triggered by a signal, or I didn't find anything that will really trigger the activity of this kindness.
Actually, it's a balance between kindness and phosphate. So maybe
very likely.
What is the phosphate?
We don't know. It's probably PP2B. We don't know exactly what kind of phosphatase. What?
Look at the repeat in the promoter to find what activates the kindness.
Okay. I'll tell you frankly, our direction are now more in the pattern of firing and what happens in terms of the mechanism. Okay, with the kinase, but microtubules. We are looking now for a super resolution microscopy in order to see what happens. Yeah.
You said the kinetics of the APSC change. Is that a change in the composition of the active receptors? 2R, 4R, or something like that?
No, we looked for that. We have the same kind of rectification. I mean, there are glue R, the glue R2, the classical. Okay. Sodium one. Yeah.
So, can you say how come the shift of both of the channels together leads to decreasing stability? Because Martin Cole showed that in the action segment, and as I mentioned in notes from here, they're together in order to enhance sodium channels and action potential.
But mostly in node of Ranvier.
Right.
Not in the axonal segment. In the axonal segment, we don't know exactly, actually. And here, we have really a decrease in the excitability. Yeah.
Maybe related to the first question, the modulation of the kinase. Maybe dopamine modulates this balance between the kinase and the phosphatase. I say because there is one article that says in Parkinson, some cells that has IM has a change. The proportion that has IM change in the striatum at least. So.
Well, in spinning neuron?
Sorry?
In spinning neuron?
No, cholinergic.
Oh, okay.
So the proportion of cholinergic that has IM.
That's possible.
So
That's possible.
maybe one possibility is that.
Yeah.
Can you speculate about the importance of this mechanism of the initial action segment translocation in vivo and which conditions it would
Of course, this is I address the question of Adi. I cannot talk about much, but I have a paper to review where they have kind of behavior, and they do see in behavior change in the axonal segment. So this is something which is it looks quite strong. So there is a kind of link between a behavior in the adult. This was done in mice, and they have change in the location of the axonal segment. They didn't look specifically for the channel. They labeled the ankyrin gene, okay, but it reflects more or less the location of the. So it should be kind of important for. And we know, for example, in adult under epileptic condition, there are changes in the location of the axonal segment. under autistic condition. You know, in Haifa, no. Hanoch, בדיוק. Hanoch find in his mice, he has mice, the Engelmann syndrome model for mice, and he do see in adult animals that there are, I think the axon initial segment is longer. So they are, of course, the plasticity is much stronger during development, but I think they are in a dynamic move in adults under different environmental conditions. So
I lost a master's student spending 2 years on this, and we did deprivation, couldn't find any difference. The cortex, somatosensory cortex deprivation. But Matthew Grubb tells me
Cuba, I find
development.
still development, but no. You know, intuitively, you are right that during development, this location is much more plastic. But under adult condition, in mature condition, there are changes.
I'm not challenging anything that you said. It's fully kosher. Yeah, we're looking in the factory vault. That's huge.
Yeah.